Okay, let's make a start. Once again, in week 4, the projector's still not working, so we'll have to shuffle backwards and forwards between the two. So I want to move on to a slightly different subject now. I've talked a bit about sort of the big picture, and I've talked about atmospheric dynamics, how we mix things around, what sort of species are present, what sort of length scales that they vary over. Now I want to talk about a little bit about some chemistry and get into some detail of the sorts of processes that we observe going on in the atmosphere. So, the first thing we need to realise is that chemistry requires things to react, and if you want things to react with each other, then you need some mechanism of creating a reactive intermediate. Okay. Now, typical bond strengths of the order of some hundreds of kilojoules per mole, as I'm sure you're well aware now. So, for example, the bond dissociation of O2, the dissociation energy of O2 is 495 kilojoules per mole. The dissociation energy of a CH bond and the dissociation energy of an OH bond, they're of the order of about 400 kilojoules per mole. So if you've got an atmosphere that's full of different chemical species and they're all neutral molecules, then starting some chemistry going is going to be quite difficult. So if you're looking about the thermal energy, so thermal energy, if you go back to your law of equipartition of energy, that tells us that at some given temperature, the average energy is of the order of 3/2 RT, where T is the temperature. And if you work that out for standard ambient temperature and pressure, you find that that's around about 3.7 kilojoules per mole. Standard ambient temperature and pressure. Okay, so that's a factor of 100 too small to get anywhere close to being able to break bonds. So we can't make chemistry go in the atmosphere by thermal energy. There's only one thing that's got enough energy to start things like that going, and that's sunlight. So only photochemistry has the potential to start reactions. So for an example of that would be if you take 300 nanometers, convert that into kilojoules per mole, that is equivalent to 380 kilojoules per mole. So this is the edge of the UV. So what this implies is that only UV light can break bonds. Now there are some species that can be photolysed at longer wavelengths, and we'll talk about those. But typically we're talking about the higher energy end of the spectrum, UV light having enough energy to break different bonds. So there's no way that we're going to be able to break things like OH and CH bonds with the sort of light that's present in the atmosphere. That's only going to happen when there's UV. So we need to think about how other species might occur and how other species might be photolysed. Okay, but there are some species which have bonds that can be broken by light in the visible, and in particular there's a species that can have its bonds broken by light in a just about accessible region of the spectrum. So ozone has absorptions in around about 320, down to about 320 nanometers. So typically what can happen, so we might have ozone plus photon, which gives us an O atom and O2. It's this bit here, which is a reactive species, we can then go on and do subsequently some more chemistry. Okay, so this reactive species produces another species, the OH radical. And OH is an aggressive oxidant and will react with just about everything else in the atmosphere. And we'll talk about detailed chemistry in a while. So, if we're going to look at photolysis of species starting chemistry off, then we need to know something about the wavelength of light that's present in different parts of the atmosphere, and we also need to know about the intensity of the light. So, as a result of atmospheric absorption and scattering, the intensity varies. Widely. So at any given point in the atmosphere, we need to know exactly how much light is arriving at what sort of wavelength. And this is defined by what's known as the actinic flux. I'll show you a figure for that. So this is figure 14. And what we've got for this is we've got a definition, sort of like a diagram to show you definitions of where the things come from. So this is like a region in the atmosphere, okay? So it's a certain distance above the ground, so here's its altitude. And what you've got is you've got four different kinds of light irradiating this atmospheric slab. So the first thing you've got here is direct solar radiation, so this is sunlight shining on there, and as you can see, because the atmosphere has different kinds of absorptions, the higher up in the atmosphere this is going to be, the less air there's going to be to absorb the various different components. So we have direct solar radiation. What we also have is we've got scattering by gases and particles. So the second component that we have is the solar radiation arriving not directly but after scattering. So that scattering might be Rayleigh scattering from molecules, or it might be scattering from particles, called Mie scattering. There's all sorts of different processes that can lead to scattering. So what we end up with is two sources of illumination from above. What we also get is light reflected off the Earth's surface. So we've got reflected light. So this depends upon the colour of the underlying Earth. But what we've also got is that the reflected light can also be scattered. So the fourth component there is scattered reflected light. So at any given point in this atmospheric slab, we've got light coming from all directions, and the wavelength of all of those different directions will depend upon, first of all, what's been absorbed before it gets to the atmospheric slab, and the second is it's going to depend upon the nature of the things that are doing the scattering. Okay, so we've got all sorts of different colours, and we've also got different intensities, and depending upon where this is in the atmosphere, we're going to get different amounts of different wavelengths. Now there's one further thing that contributes to the amount of light that's arriving at any given part in the atmosphere, and that's the path taken by the direct light through the atmosphere. And that depends upon the position on the planet, and we define what's called the solar zenith angle, which is basically the angle between the zenith, which is straight up, directly above our head, and the path the sun's shining from. So that's going to depend on the latitudes. So higher latitudes have higher solar zenith angles, so longer paths through the atmosphere. So you can see that if I draw like a layer of atmosphere there, at this particular solar zenith angle, we've got the path length of this long. If we were looking at the sun directly, if I follow this around, if we have the sun directly illuminating that bit there, then of course you can see that path through the atmosphere is shorter. So if it's a shorter path, less absorption in the regions where absorption is going to occur. So we have processes dictating where the light comes from, and we've also got physical parameters like what angle the sun is to the bit of atmosphere that we're looking at. Okay, so it's dictated by direct and scattered light. It depends upon the solar zenith angle. And it also depends upon a load of other things. It depends upon the season, depends upon the time of day, it depends upon the presence of scatterers, e.g. clouds, so we're going to have a very complex dependence of light being incident upon the planet. Now, atmospheric absorptions, as I just briefly mentioned, play a major role in determining the actinic flux, because if you've got gas that's got absorption bands between the light source, the sun, and the piece of atmosphere you're looking at, then light of that wavelength will get reduced. That's good for us, because that's how ozone helps protect the planet. So a classic example of this is that ozone absorbs strongly between 200 and 300 nanometers, 320 nanometers. Sorry. So if we look at the top of the atmosphere, don't worry about the diagram on the side there. That's just for defining terms and angles that we're interested in this here. Right. So what these curves show is the value of the actinic flux versus wavelength. And I will talk a little bit more about this in detail in a minute. But what you can see is this curve here this is at 50 kilometers, so this is effectively outside most of the atmosphere. So you can see that the actinic flux on a layer 50 kilometers up in the atmosphere has a value of somewhere around about 5 times 10 to the 12. And if you look at the units here, it's photons per square centimetre per second in a 1 nanometer bandwidth. Okay, so this is quite a lot of photons. At any point here, you can see that in the 200 to 300 range, they are of the order of about 5 times 10 to the 12 photons crossing a 1 square centimetre of atmosphere per second in a 1 nanometer wavelength. So if you look across that, there's 100 nanometers across that, so there's 100 times that across the wavelength range as well. Okay, that's quite a lot of material, but you don't have to go too far down in the atmosphere before you see that starting to attenuate. Now, because of ozone's absorption spectrum, which we shall look at in a second, we start to see let's go to some multimeter to a different colour. We start to see at this point here there's an attenuation. So at that point here we're down to 10 to the 11 for the actinic flux. Oh, brilliant. And if we go down to 30 kilometres, you can see that 30 kilometres have taken a big chunk out. Of course, actually, this diagram really goes down here somewhere at 30 kilometres. And when we get down to 20 kilometres, I'm going to go back to my red pen so you can actually see it. When we go down to 20 kilometres or even lower, what we start to see is this band here is effectively going to zero. Okay, so if we extrapolate this scale down here, we've got to the point where that's zero. Now that's a good thing, because all those photons between 200 and 320 nanometers are just the right wavelength to photolise bits of your DNA and start causing mutations and things like that. So this is what the ozone layer does, is it effectively cuts out all of the UV that is present in the emission spectrum of the sun. It stops it reaching the ground. So the fact that it stops it reaching the ground is good for biology, but in terms of understanding atmospheric chemistry, we need to know exactly how much UV light in this wavelength range arrives at different altitudes in the atmosphere. Because if, for example, we have some molecules here at 20 or 30 kilometres containing carbon-hydrogen bonds, carbon-carbon bonds, things like that, specifically carbon-chlorine bonds, this is the origin of the polar ozone hole, then things in this region can easily be photolised. So at 40 kilometres, there's plenty of solar flux. For example, for photolysis of CFCs, chlorofluorocarbons, which we'll talk about later. And this is the origin of chlorine species, the odd chlorine species which cause polar ozone depletion. So CFCs don't photolise down at the ground because there isn't enough solar light, there isn't enough photons with enough energy to do that, but they certainly photolise relatively easily in the upper atmosphere because there's nothing to stop the UV getting at them. Okay, so the ozone layer effectively absorbs all the 200 to 320 nanometer photons before they get down to the ground. molecules can easily be photolysed at higher altitudes, and this is one of the reasons why I told you that there isn't really much chemistry going on above 30 or 40 kilometres. That's because almost everything above that has been reduced to atoms and radicals by photolysis. And the density is very low. Okay, so the next thing we need to consider then is to refresh your minds. So it'll be fresh in some of minds rather than others, because you've adjusted a course on photochemistry with Sven last semester. Just to refresh your mind, we need to think a little bit about photochemical processes. Okay. Now the principle of this relies upon the fact that the absorption of one photon by a molecule, if it's of the right wavelength, can create an excited state. And if we've got an excited state, then we also need to consider what are the possible fates of this excited state. Now these are all the things that you've seen before. So we start off with our molecule AB plus H nu. And this is the absorption process. And then you'll recall that there are a whole possible number of different kinds of outcomes for the fate of this thing. It can luminesce, so it can drop back down to the ground state and re-emit a photon. So this is fluorescence or phosphorescence or the various different luminescence processes. It can transfer the energy to another molecule. It can collide with something and lose the energy. If it's of high enough energy, it can ionize, it can fall apart. You need quite a lot of energy for that. It can do things like it can isomerize, or it can then do reactions. But the thing we're most interested in, because the thing it does most often in the atmosphere, is it causes dissociation. Now, this diagram's not quite right, because there should be two little dots on there, because usually what this falls apart into when we get photolysis is radicals. Okay, and just to refresh your memory, in case you've forgotten, each one of those past paths has what's called a quantum yield, a specific quantum yield. Because the way that the whole quantum mechanics bit works is one photon gets absorbed, excites one molecule, and that one molecule can then do a number of different things. But one molecule can only do one thing. So the quantum yield tells you the approximate proportion of molecules that go down each of these individual channels. So, for example, you'll remember that the sum of all primary... I'll write this down on the thing so we don't lose it thinking about it. So there are several possible fates. There are several possible fates of the excited molecule. Luminescence, dissociation, etc. Each channel has a specific quantum yield. This is the probability. There are many ways to define this, but a good way of thinking about it in this context is it's the probability of the molecule going down a specific channel. The thing you also have to remember is the sum of all primary quantum yields must be 1. So what that's saying is if there's a probability for each of those channels, it must all add up to 100%. So you might have 90% going down one channel and then 10% going down a second channel or something like that. But you can't have a primary quantum yield greater than 1. And you must have all of the quantum yields and they must all add up to 1 as well. You can't have like a primary quantum yield of 0.9 because that means there's 10% missing and you can't do that in quantum mechanics. So the primary quantum yield tells you how efficient a different process is, and we're particularly interested in the quantum yield for dissociation. Okay, so initially we're principally interested in the quantum yield for dissociation. So we have AB, so H nu goes to AB star, this goes to A plus B. Just to indicate that these are radicals. Or reactive species anyway. We'll see in a minute what I mean specifically by that, because you can also photonize something where one gets both of the electrons and the other loses 2 electrons. Depends upon the nature of the species. We'll talk about that when we look at it in detail. Because what we've got is we've got the actinic flux, which tells us how many photons are present at the right wavelength. If we combine that with the quantum yield for dissociation, that tells us how many dissociated molecules we're going to get. So let's go back to our picture again. So what we've got here, this is the absorption cross-section. Okay, so it's defined in terms of a cross-section. This relates to epsilon in the Beer-Lambert law, of course. So epsilon is the molar extinction coefficient. Sigma is effectively the molecular extinction coefficient. So you can get from epsilon to sigma to Avogadro's number, more or less. A bit of units to muddle about with as well to get the length scales right. So the cross-section, sigma, is in centimetres squared per molecule. And a big sigma means a big epsilon. So if something's got a big sigma, that means it's got a big absorption coefficient. So this is the electronic spectrum of ozone, and you've got this one here. This is called the Hartley band. This is a big, strong absorption, and this is the one that goes from 200 to 320 or so. Okay, so it's absorption in this particular electronic state that we get. But there are others, but they're very weak. You can see this is a logarithmic scale. This one here, the Chapuis band, is quite strong at 600, but it's around about 1,000 times weaker than the height of the Hartley band. So this is the main absorption in the UV. So this is the absorption spectrum. So that's this is the AB going to AB star bit. And the next thing we need is the quantum yield. So that's this. So that tells you the fraction of molecules absorbed at that wavelength that then end up coming out as a different molecule. Now, this reaction here that we're dealing with is its ozone plus H nu goes to O plus O2. But it's not as simple as that. You'll notice that there's a symbol here. It doesn't say O, it says O something. It says O, and it's got a singlet D. Okay? Now you'll recognise this as being a term symbol. And specifically what we're interested in here is that this is an excited O atom. I shall put some notes about this in a minute. So the other thing that we've got to think about is we've got those different absorptions, but many things have different they've got lots of molecular orbitals, so you get an absorption from the highest occupied molecular orbital. You don't necessarily have to go to the lowest unoccupied molecular orbital. There's loads of other possibilities, and some of them are more favoured than others, depending upon the selection rules and all sorts of stuff like that. So it is quite possible to create more than one species. Now the reason I'm showing you the quantum yield for O singlet D production is this is the reactive one. There's another possibility, which I'll put some notes on. What you also might have is you can produce, the two species are O singlet D is an excited state. The other version of this would be oxygen. The ground state is triplet P. This is the ground state. And it turns out that this is very uninteresting, so it doesn't really do much. So we don't want the quantum yield for the production of O triplet P. We want the quantum yield for the production of the excited one. And if you look, you'll see here's 1 on our scale, but you'll see that 1 on this scale isn't where all the numbers lie. So there's a gap there. And that gap there represents the quantum yield of the sum of the quantum yields of all the other processes, and some of that is luminescence, re-emitting the photon, but actually most of it is O triplet P production. So we're interested in the reactive species and the quantum yield. We might have a quantum yield for different products of dissociation. So there isn't just one dissociation channel. I'll put some notes up about that. So there may be more than one dissociation channel, so the ozone may dissociate to this to give this one, or this one. And it turns out that we're specifically interested in the ground state. I just remembered it's funny how you forget things in the heat at the moment. I can't remember what the ground state term symbol for O is. It's triplet sigma U. Of course it is. So these are excited states. So these are effectively, they're hot, and these are ground state. The main reason for this distinction is that O singlet D being reactive pulls a proton off water, which is 2 OH radicals, but O triplet P doesn't have enough energy to do this. So we're not interested in O triplet P because as far as we're concerned it doesn't really do anything. Okay, as we shall see in the future, the majority of atmospheric chemistry is driven by radical and reactive photoproducts. Now we shall see as we go through looking at the chemistry that most chemistry follows a specific pattern. Most radical chemistry of this nature does. This isn't specific to atmospheric chemistry, but it does. It is prevalent in atmospheric chemistry, so we'll have a look through this. And to save you writing all of this down, I'll put it on a nice slide for you. We'll just wait until people finish scribbling, then I can change. And that's this. So here are the 4 steps of atmospheric reactions. So this is what we've been talking about here. The first step is initiation, the generation of something, mainly through photolysis. So here's the hot species. What we've also got is in the wrong order. Right, okay. I want that one first. I might have to put these in the wrong order on the slide. That one's the second one. So initiation is the generation of a reactive species. Threw me for a second there. Then we have what's called branching, and branching reactions increase the number of reactive species. So in this place we've got O singlet D reacting with water to give us 2 OH radicals. The third thing that we see, which we shall look at in some detail in the chemistry sections, are propagation, where we have conversion between radicals, an exchange of things. So here's a classic one. We'll be seeing much more of this one in the future. OH is very, very reactive, and it would prefer not to be OH. It would rather be water again. So OH will pull a proton off virtually anything that's got a proton. It can pull a proton off water as well. There's an equilibrium, but then that doesn't make any difference. It still makes an OH radical. But the thing it does is it always pulls a proton off this, because the proton affinity of this is much greater than the carbon-hydrogen bond strength. So we end up with another radical, in this case the methyl radical. So it's a new radical, but it's a bit less reactive. Okay? So we lost a little bit of the energy in the scale there. What we actually find is then we have a chain of reactions to follow. We'll look at that in the later lectures, where these radicals then go on to do other things. So here's another example of a radical reaction, but this is a radical-radical reaction, and one of the things a radical-radical reaction can do is it can exchange oxygenated species. So this, you see this happening quite a lot, oxygen shuffling, but we'll see that again in the chemistry as well. Okay, so the final thing that we have in any kind of a radical reaction is what we call termination, and this is the termination step which causes the radicals to become deactivated. And here, this is the classic deactivation method for OH. There are several of them that OH can deactivate by colliding with quite a few of these other different things to produce this species here. So this is a neutral, stable species. Now, some of these neutral, stable species are only a little bit stable, and they can quite easily be photolysed back into the reactive species. And when you have a species like that, it's sometimes called, we'll see these again, a reservoir species. So for example, you might have OH and NO2 sticking to react together, and then the nitric acid is held in some kind of form where it's not easily photolysed, it's dissolved in a liquid or something like that. Then when the droplet evaporates, you get nitric acid coming back into the gas phase, they'll get photolysed back into the different radicals. but in the interim it's acting as a reservoir, so it's holding some of that reactivity locked up. But the termination of the radical chemistry occurs by the formation of this species, whatever happens to it subsequently. So we've got 4 different things. We have initiation, then we have branching to produce a number of different reactive species, we have propagation, and this is where much of the chemistry occurs, and then, because we can't have an infinite number of radical cycles, the stuff there to stick to and react with, then we get the death of the radical. You'll notice incidentally that I haven't, what you might guess would be the most obvious thing here would be OH plus OH, but of course what we shall subsequently see is because OH is so reactive, the instantaneous concentration is so low that a bimolecular reaction between 2 OH radicals is almost impossible because they're present in such a small quantity. We'll talk about that later. Okay, let's go back to the visualizer. So again, on that slide there, we've got initiation, branching, propagation, and termination. Okay, so the principles behind this are the same for all radical chemistry. And those of you that have done polymer units will have seen things like this before for radically initiated polymerization reactions. They do the same thing. So the next thing we need to look at is we need to look at reaction kinetics in the atmosphere. And figure 20 on your slide, which I'm not going to bother putting up because it's a bit scary, is, well actually I will show you because I'm just going to go run through some of the main principles here, but I'm not going to go through it in detail, it's just a reminder as much as anything. This is a summary of unimolecular, bimolecular and termolecular reaction kinetics, so that the first one's showing you the rate equations and the sorts of examples of things that do that. The second one shows you a bimolecular reaction and all the various different kinetic equations to do that. And the third one's a termolecular one. So I'm not going to go through that in detail, it's just something that's there to aid your memory when we come to do some actual kinetics with this. You'll find when we come to look at some of the problems associated with this, it's probably a good idea to read through your kinetics notes because this is relatively simple, but if you can't remember it, it'll hold you up some of the stuff we're going to do next. So go and make sure you know all about that. So reactions in the atmosphere, they tend to be elementary reactions. So by elementary reactions I mean reactions which occur in a single step rather than in multiple steps. The reason being that in gases in dilute solution, I mean the gases trace gases in a large atmospheric volume, they're quite a long way apart. So the possibility of a reaction mechanism involving A going to B and then B reacting with C to go to something else and C reacting with a third thing to go to something else, they're reasonably limited. There's only a small number of reactions where you do get kinds of complex mechanisms, because usually when these things are formed, they're formed so far away from everything else, like the next stage of a reaction, that it's difficult to get complex reactions. Okay, so complex reactions are rare due to dilution. So if you look at all those kinetics that you've done before where you've got multi-stage processes, then that's not really going to happen in the atmosphere, except in some limited cases. So we have unimolecular. It's usually decomposition. So an example would be something that we observe quite a lot, as you shall see. this species. So this is peroxyacetyl nitrate. And what this does is it's very unstable. It wants to fall apart, and it falls apart into a peroxyacetyl radical and NO2. So this is one where we've simply got a simple rate equation. So the minus D concentration of this stuff's called PAN, by the way. You'll see this before. So it's just a simple unimolecular decomposition, first order. Okay, so we also see bimolecular reactions between two reactive species, so an elementary bimolecular reaction, and an example of a typical bimolecular reaction would be OH plus our hydrocarbon. So this is an alkyl fragment, to give you H2O plus R dot, and then minus concentration of OH dt is equal to K concentration of OH, concentration of RH. So this is a standard bimolecular reaction, and below shows bimolecular things. Now, termolecular reactions between reactive species are pretty much unknown. And the reason that they're very rare is if you've got a trace species present at 1 part per billion, and then another trace species present at a concentration of a part per billion, and then you want them to react with a third species which is also present at a part per billion, then you're looking at something which is really vanishingly unlikely. However, what we do often get is we get a termolecular reaction involving two reactive species plus a third body, as we call it, common. So we might have A plus B plus M reacting to give to give products plus M. And what we've got here is this is a trace, this is trace, and this is high concentration. And the purpose of M is to take away excess energy. We've probably seen this before. The classic example of this is O plus O2 plus M gives ozone plus M. Because what happens is, in a standard reaction, if you take ozone and an oxygen atom, to give ozone, put a little dagger there, so it's highly excited. Okay, so if you think of this in terms of potential energy diagram, so we've got, here's potential energy, and here's our O to O distance. What we have is the potential energy curve for ozone looks like this. But if we form our ozone, when these things come together and react, it's formed with high energy. what's going to happen is we form our O2. So that bit there represents the formation of that species, the highly vibrationally excited species. What's going to happen is it's just going to fall straight out of it because it has more than enough energy. It's got more than enough potential energy to break the bond. So it'll just fly straight out of that potential, and it will dissociate. Okay, so if you imagine that, it'll drop straight back, but it's got more than enough energy to overcome the bond dissociation energy, so it'll just fly back out as O plus O2. However, if at the moment it's formed, there's something near it, then what we get is we get O3, and the M takes the energy away. So then we end up with this, with enough energy to stay trapped in the molecular potential, and all this excess energy has then been kicked out with M. The reason why you need to know about this is this is really, really important in lots of atmospheric chemistry reactions, because radical reactions usually produce species that have got bucket loads of energy that they need to get rid of. Now it turns out, what are the two species that are most common in the atmosphere that are likely to be M? It's usually nitrogen or oxygen, because it's present in vast excess. And we'll see when we look at some particular reactions that this is crucial for atmospheric chemistry as a whole. Okay, let's leave it there. I'm sure Peter Hood wants